So far, we talked about what linear regression is, how you do it, and then after you do it, the final step is really making some description of how good is this fit. In other words, how much of the variability that you see in the original values is explained by the regression. So that's where we're heading. All right. So again, this is the problem. We're dealing with scatter plot. We're trying to draw a line that will essentially we can use to predict our dependent value based on a measurement of the independent value. In this case, this is an example of what when we ran before. We had 5 measurements that the blue dots. They show the number of hours studied and then the grade in points of value. Actually, this graph is not exactly the same as this equation, so don't get confused by that. It was correct in the previous lecture. And this was found, this 6.38, the 27.31, was found by minimizing the standard deviation of the departures from this line. In other words, the distance between, vertical distance between each of the measurements and where they intercept that line. Okay, and the smaller the values, the smaller the standard deviation, and the better of a fit that you're going to end up with. Question is this a good fit? In other words, are we happy with this fit? And we're going to come up with this thing called R squared, which is essentially the fraction of the uncertainty explained by the regression function. So you have some initial uncertainty. Say you take a student and you don't know how many hours they studied, and there would be that uncertainty might be explained by the or characterized as the total variance. Remember, the variance is the square of the standard deviation. After the fact, we end up with a variance or a standard deviation of our departures from this line, and hopefully that's going to be smaller than the original total variance. So let's talk about that and explain what I mean more. So these are the 5, those same 1, 2, 3, 4, 5 students. And in this case, what we're measuring, what I'm showing you here are the departures from the absolute mean of those 5 values, right? So it's, in this case, essentially a horizontal line. And then we can calculate the standard deviation and the variance of that. So that's what we call the total uncertainty, or the variance for the departure from the mean value. In other words, that horizontal value. Now, if we're going to calculate, what we're going to do in a minute is calculate the variance about our predicted value. And hopefully that's going to be smaller than the total variance. Otherwise, you're not doing a very good job. So here it is, this blue dot, that is essentially my predicted value. And then the departures are these little green arrows. And if we find the variance of those values, in this case, the variance equals 136 points. And previously, the variance about the mean was in excess of, say, 300 something. So the R squared value is just going to be this variance divided by, this explained, let's go into here in this slide here, which is 1 minus the unexplained variance over the total variance. And the unexplained variance, that's the remaining variance about my regression line. In other words, the line that I come up with a regression. And we're minimizing that standard deviation. So if we take the square of that minimized standard deviation, that's that unexplained variance. It's how much sort of variance is still, like, we just can't really get our hands on it based on that one measurement of the number of hours that the student studied. The total variance is just the variance in the about the mean of the grade of or on some exam endpoints. Now we can just do some simple algebra, and we end up with 1 minus. We just take the total variance over the total variance multiplied by 1, and it's just like multiplying by 1. So essentially, I hope you can understand that this is essentially the same as that. And so what you end up with here is that the total variance minus the unexplained variance is essentially the explained variance over the total variance. Now, hopefully, if in a perfect world, if the regression line fit all the data points perfectly, then the explained variance would essentially be the same as the total variance. Okay, so a value of 1 would be essentially a good value that you would say that's a really good fit. All right, so in our example, the total variance was 372 points squared. The unexplained variance, or the variance about our predicted value, in other words, the variance of these departures about the regression line, was 136. So the explained variance was 236 points. So the R squared equals that explained fraction, which is 236 over 373, or 0.63. So obviously this R squared value can go from 0 to 1. So 0.63 means essentially that 63% of the variance has been explained by our regression line. All right, so I'd like to look at a few additional things that you need to watch out for when you're doing a linear regression. R squared is not the entire be-all and end-all of linear regression. So occasionally you'll end up with outliers. You may have measured data that you look at it and you go like, why is it? What is this? Why is this over here? You know, it doesn't really go with all the other data. You may end up throwing it out. You may say, well, that measurement probably isn't good, or something else was affecting the data that's not consistent with whatever's causing the data to be what it is for the remaining data points. So you may throw it out so you can remove the outlier. That's just one thing to watch out for. Another thing is what we call heteroscedasticity. Oh my goodness. Essentially means if you have a variance about the departures. Say you're going to draw a predicted value. Let's see if I can draw a straight line. It's not very straight. But then you're going to have you measure your departures. If the variance of the departures increases over one region, in other words, over here it's greater than this region, that's called heteroscedasticity, and that's essentially violates some of the underlying mathematics or assumptions of linear regression. Another thing to watch out for are data for which you're doing a force fit. So you might have data like this one here that probably has some physical relationship that's causing this curve to occur, and you just force fit a straight line through it. So particularly if you start extrapolating out here and say, well, what is y2 when x2 is 18? Not a good idea. Probably linear regression is not the right technique to use for that line. Again, here's another problem where you have a lot of data right around 8, and then you get one data point up at 18. Is that really a good regression line for that data? I don't necessarily think so. Here's the case of an outlier. We already talked about that one. And this first one, that's sort of the classical, not bad set of data points. This is upper left. So make sure you plot your, these are called scatter plots. Make sure you plot them first so you have some sense of the data that you're looking at. We've just barely scraped the surface. This is a big, big topic. You could spend weeks learning linear regression techniques. There are other additional tests that I'm not going to go through that we haven't really dealt with as yet. But this, hopefully you got a good introduction of linear regression, how to do it, and then how to make some evaluation of the results.